Hi, Samantha. So our goal for today is to put an error bound on the remainder when we estimate with a Taylor polynomial. Our story so far has been that we have a function, f of x, and we wish to estimate it with a Taylor polynomial, tk. And what we found on Friday is that tk is equal to the sum from n equals 0 out to k of the nth derivative at c divided by n factorial. Those are our coefficients. Times, here's our polynomial, x minus c to the n. And c is the center. So the full name of our polynomial is t sub k of x centered at x equals c. And we only call it by its full name when it's in trouble. And so this approximately equals bothers us because we wonder how good is the approximation. And we recognize that there will be some kind of error, which we call the remainder, so that f of x will be exactly equal to its Taylor polynomial approximation plus the error, which is a function of x. So for each different value of x, then we will have a different amount of error, and we call that the remainder as a function of x. So if we were lucky enough to know all of our function values, then we could find the remainder just by subtracting it. But unfortunately, that's rarely the case. If it were, then there would be no point in estimating with a polynomial. And so our goal is to be able to say, even if I can't find the remainder, what I'd like to be able to do is to put a bound on it so that I can say that the magnitude of the error is going to be less than or equal to some expression. By the end of today, we will have developed what that expression is, and I'm going to go ahead and give you the result, which looks a little strange. It's going to be less than or equal to the maximum over all t's in the intervals from c to x. And there's going to be three components to our error bound. First of all is going to be the k plus 1th derivative evaluated at t. So really what we're going to do is to go on the interval from c to x, and we are going to search through for the t that gives us the largest value of the k plus 1th derivative. And then we're going to take that value, and we are going to, well, let me actually write it like this. And we're going to multiply it by the factor x minus c to the k plus 1 and divide it by k plus 1 factorial. This is going to be our error bound, and it's commonly called the Lagrange form of the error bound. In the lecture notes for today that I put up on another last night, I gave you a little bit of historical information about Taylor and Lagrange. Now, let me show you how this is used first, and then we'll come back to a proof for the whole thing. So let's do an example here. What we'd like to do is to estimate, let's say, e to the x with a third degree Taylor polynomial, and then we'd like to know, let's estimate the value of e to the 0.1. With a third degree Taylor polynomial, centered at c equals 0, centered at x equals 0. And then once we have estimated that, we're also going to find a bound for the error in this approximation. So there's two different questions here, and we're going to answer one question with T3, and we're going to answer the other question with the remainder. Does the question make sense there, Ryan?
Can I just, I see the f of t in the
Yeah.
absolute value sense. What's the x?
So this exponent is actually the number of the derivative that we're taking, and we're taking the k plus 1 derivative. So in a lot of ways, this looks like the form for just the next term, right? But the difference is that instead of evaluating directly at x or directly at c, which I would do for the next term, I'm going to be finding the maximum possible value over all t's between c and x. Okay, so the first part, the T3 part, we're pretty good at. We have enough experience with e to the x to be able to come up with its Taylor polynomial pretty quickly. We know, you may remember the Taylor polynomial for it. If you do, you can go ahead and directly write it. I hope that you do. But if you do not, you can compute it by hand by generating the derivatives and then evaluating those at the center so that I get 1 for all of those derivatives, and then I can get my coefficients. A sub n is equal to 1 over 0 factorial, which is 1. 1 over 1 factorial is 1. 1 over 2 factorial is a half. And 1 over 3 factorial is a 6. So that my estimating polynomial, T3 of x, is going to be 1 plus 1 times x plus a half of x squared plus a sixth of x cubed. And all of this process, I think, is pretty familiar at this point. If it's not an automatic thing, then you want to practice it sitting board in English class, okay? 4th degree Taylor polynomial for e to the x. Go. And once you've done it a couple of times, it'll be fine. If you haven't done that, make sure you do that soon. Okay. Now, what about the remainder? What about our point, actually? We want to estimate e to the point 0.1, so we're going to use our Taylor polynomial to estimate. And for some reason, my smart board is not smart today. Okay. So that would be 1 plus 0.1 plus a half of 0.1 squared plus a sixth of 0.1 cubed. And off the top of my head, I don't know what that is, but let's actually get a decimal estimate for that. Okay, there we go. So, and I get 1.105105.2. That is the estimate. Okay. Now the question is, how good is this estimate? And the remainder is going to tell us that. It's going to tell us a bound on the error. And so we are going to say that the remainder is bounded by. Please notice the notation here. This is the remainder for the 3rd degree Taylor polynomial, and it's the remainder at 0.1, at x equals 0.1. And it's going to be less than or equal to the max for all t's between the center and the x value that we evaluated at. of the fourth derivative of t times the constant factor 0.1 minus 0 over 4 factorial. So notice that these two factors right here depend only upon the point of evaluation. There at x equals 0.1. So if I were to get a number line going here, what I'm doing is I am going from my center C, and I'm going all the way out to my point of evaluation. And I'm going to compute that distance right there. That distance right there is the distance that goes in right here. And then I'm going to search through all possible t's in here until I find the t that gives me the largest possible value for that fourth derivative. And the reason I want the largest possible value is that I'm doing a worst case analysis. In reality, as we shall see when we do the proof, there is a t somewhere in here that makes this expression exact. So the actual remainder at point 1 is equal to f4 of t times blah, blah, blah for some t somewhere in here. Unfortunately, I don't know which t. And so because of that, I take the worst possible case, which is the maximum, and I say that the error can be no worse than that worst possible case. Is that logical? So the only question then is, how do I maximize this? And we have a bonus. And the bonus is that our function is easy to deal with. What is the fourth derivative of e to the x? We evaluated at t. E to the t, that's right. And we have a double bonus because e to the t has the characteristic of being an increasing function, which means that as I go from 0 to 0.1, e to the t just gets larger and larger and larger. And therefore, my estimate is, my maximum is going to be e to the 0.1. And that presents us with a slight problem, because my job was to estimate e to the 0.1 to begin with. Right? And so I wonder, what could I use as a bound for this error? But it seems to me that if my Taylor polynomial estimate is something like 1.1, then I should be reasonably justified in taking a value that is certainly less than e, again, increasing function, and e is certainly less than, say, 3. E is 2.718, just to refresh your memory on that. So I could use 2.718 as a suitable bound for that. That would be a conservative bound. I know for sure that my error is less than that. Or I could use 3 if I can't, didn't feel comfortable with that. Let's use 2.718. So this guy is less than, way less than, actually, 2.718. And when we compute that, that turns out to be you'll want your calculators out and computing along with me, otherwise it just gets kind of boring. And that error bound turns out to be really nice. It means that to 4 decimal places, my expression here, my Taylor polynomial approximation, is exactly correct to 4 places. That's pretty impressive. And sure enough, when we actually compute e to the 0.1, we get 1.1051709, which agrees with this to 4 places. Now, keep in mind, places where students will mess up. First of all, they will try to plug in x for t, right here. We ended up using t equals x here, but only because we knew that e to the x was an increasing function, and therefore its max is right on the end. Second place where students will mess up is they'll assume that the remainder is this value instead of is bounded by this value. So keep in mind that the remainder will be less than. For some functions, for many functions, the remainder that you get here is kind of pessimistic. The error bound is kind of pessimistic. It way overestimates the amount of error that you actually have. Does that make sense in terms of how to use it? Yeah.
So, if it's not that easy to find the max, do you have to like take another derivative or something?
Yeah, if it's not that easy to find the max, what you do is use what you know about the function, anything you know about the function, to give some kind of bound on it. And mathematicians use the word tight and then correspondingly loose, of course, to indicate how much play there is in the bound. If I have a lot of information, then I can give a tight bound, and I'll know something pretty definite about that error. And if I don't know a lot about the function, there it is. So for example, if I'm working with functions sine and cosine on random intervals, well, I know for sure that sine and cosine have a maximum of 1 on any interval, a maximum possible value. So a lot of times I'll just directly go for 1 for the sine and cosines. For other functions, you've got to use what you know. Here are some things to help you though. If a function is increasing, its maximum will be out here. And if a function is decreasing, its maximum will be at C. If a function is concave down, its maximum is guaranteed less than its tangent line. So that's about half the functions right there. So those kinds of things can help. Yes?
Can you explain again why you went from the E to the 0.1? Yeah.
Oh, yes. Okay, good. So this is an example of Charlie's question. Our original question as posed basically asks us to pretend that the e to the x button on our calculator is broken. So we can't just plug in e to the 0.1. We have to estimate it with a Taylor polynomial. And having estimated it, we now wonder how good is our estimate. So we compute the Lagrange for the error, and unfortunately we find that it requires us to know the very thing that we didn't know to begin with. So what we did was we took a value of e to the x that we knew was definitely bigger than this guy, and plugged it in right here. I myself would have gone a little tighter, and knowing that this is pretty close, I would have said that e to the 0.1 is definitely less than 1.5. But I don't have a mathematical justification for that. It's more like experience. So I would do that as an engineer, but I would not do that as a mathematician. This is a mathematically certain thing. That's a really good question. Okay, so let's actually talk about the proof. And the proof will give us some insight as to the nature of the remainder, and it will connect to stuff that we already know. And then we'll do examples. If we don't get time for the examples, then the lecture handout walks through 3 different examples, including one in which the question is badly formed. Before we get into proof, I want to remind you of the mean value theorem. Remember the mean value theorem. If f is continuous on the closed interval, differentiable on the open, I'm going to write the mean value theorem in terms of the numbers c and x here, so that it kind of sets us up for what we're about to do. We used a and b when we stated it before. then there is a t somewhere between c and x such that f prime of t equals f of x minus f of c over x minus c. Ta-da! All very fun. And you may even remember the proof for that. Our proof relied on creating a helper function. And our helper function was specifically our function f minus its tangent line approximation, which was, in this case, let's use t for our variable so we don't use that. So let h of t equal f of t minus, and then we wrong. There we go. Yep. So we let h be our tangent line approximation. And then we observe the following facts. That h of c was equal to f of c. And h of x cancel, was also equal to f of c. So what we had done pictorially was to take our function f and subtract off the tangent line, subtract off the secant line, there we go. Subtract off the secant line so that h measured the distance between f and its secant line, and that distance basically gave us f of c at e. And now because h of c and h of x were the same value, we were guaranteed that somewhere in between Raleigh's theorem there was a horizontal tangent. Because my function's continuous, it has to have an absolute max and an absolute min, and one of those has to be in the interior, therefore we get horizontal tangent. Yeah?
What about saying x equals an h of t plus it's supposed to be t?
We have this one. Yeah, these are t's here, and I'm doing this only because I want our x and c to mirror what we're about to do with our proof. So we had a's and b's in the original proof, and x's here in the original proof. I'm just changing variable names. And so since h of c and h of x are the same value, there is a t somewhere between c and x such that h prime of t is equal to 0 using Raleigh's theorem. Because that is the case, h prime of t is equal to f prime of t minus, going back up to here, our slope times 1. And since that equals 0, therefore at our t, we exactly have this guy right here. You guys remember doing this proof before?
Not this one. You can read it from there.
Does it make sense? Does the logic make sense?
I feel like you're
Yeah, I hear that. The only reason I'm doing it this way is that it's going to imitate what we're about to do for for our remainder here. So the key points are, this is going to be f minus the secant line. And then the second point is that my helper function h is has been set up so that there is an equal value at c and x. And because of that, we appeal to Raleigh. And once we appeal to Raleigh and do a little bit of algebra, poof, out it comes. Does that make sense?
The h of t messes me up with the
Because it has t, or because we just created it?
So it's like x minus c at the bottom, it's like x minus x, and then x minus t.
So t is the variable here, and x and c are constants in this particular.
But like, why is it t minus c and f of x minus c?
Oh, why did I set it up that way? Ah, I set it up so that what I was doing was a slope, an average rate of change, times the t minus c. That's going to be the equation for this guy, except for the intercept.
So what are the x minus c? Because it's
No, our variable is t. This is the t-axis.
okay, I'm just trying to figure out why it's not f of t minus f of c, but t.
Yeah, so all of this is constant. When we did the proof, we did b's and a's. So you probably saw it like this.
Probably word exactly.
Yeah. But we're about to need t's for our other proof. So I'm kind of getting you used to the idea that t is going to be our variable here, and x is going to be a fixed value. It will be constant within the context of our problem. Okay?
So after you understand the h prime equals that function.
Oh, so take the derivative here. H prime equals f prime minus constant times 1.
Oh,
Right. I'm taking a derivative with respect to t. Yep. Good. Any other questions? Okay. Now, take our mean value theorem, and we're going to view it from a way that we've not viewed it before. If we have f prime of t equals f of x minus f of c over x minus c for some t in c of x, let's multiply and add to get f of x equals f of c plus f prime of t times x minus c. I'm just taking and rewriting this. And this looks similar to our tangent line, but it's not quite because of two things. First of all, because the t right here is not taken at the center c, it's somewhere in between. And second, because we have exact equality. What am I saying here? I'm saying that f of x is equal to f of c plus an error term. In fact, what I've really done is to rewrite the mean value theorem so that it is equal to the 0th degree Taylor polynomial plus the remainder. And the remainder turns out to be in the form f prime of t times x minus c for some value of t in between c and x. Now, estimating with a 0 degree polynomial is kind of stupid. You wouldn't want to do it unless you had no information about the function whatsoever, right? So the idea here is I want to estimate the velocity curve for an automobile. So I asked the Kaglet, how fast are we going right now? She looks 50 miles an hour. So I estimate that my speed is 50 miles an hour for every single time t. Well, that's not a very good estimate. I'm estimating that it's a constant. But it's going to be, if I add on a suitable value, 50 plus some error, then it's right, because it's not very enlightening. But this now gives us the pattern for how our proof is going to go. So we're ready for our proof. Let's begin by stating Taylor's theorem. So we know what we're trying to prove here. And it goes like this. If f is k plus 1 times differentiable on the interval c to x, if my x happens to be less than c, we just swap those on x to c. Then f of x is going to be equal to tk of x plus the remainder at x, where tk is what we have done before, the sum from n equals 0 to k of n derivative at c over n factorial times x minus c to the n, our familiar construction for the Taylor polynomial. And here's the part that we're going to prove. Our error is bounded by the max over all t between c and x of the k plus 1th derivative at t of x minus c to the k plus 1 over k plus 1 factorial. What we're going to do is to prove this in a manner very, very similar to the way that we proved the mean value theorem. We're going to construct a helper function that's going to measure the distance between f and t, and we're going to apply Raleigh's theorem to that helper function. But we're not going to apply it once. We're actually going to apply it 3 times. Okay. Ready? Okay. The magic happens in our helper function. We're going to create a helper function that measures the distance between the real function and their polynomial, and we're now going to fudge that function a little bit by creating in the document I use capital K. I'm going to use M here because otherwise we are K's mixed up. I'm going to add on this fudge factor right here, M times x minus c to the k plus 1 over k plus 1 factorial. You may wonder why, but you'll see why when we start taking derivatives. And we are going to choose M as a constant so that h of x is exactly equal to 0. And since h of x is exactly equal to 0, that means that f of x is exactly equal to tk of x plus our fudge factor. And because of that, that means that our fudge factor has to exactly equal the remainder right at x. Now you say, well, can you really choose m to be that value? Well, sure I can. All I have to do is to choose m so that it is equal to the difference between f and t over x minus c to the k plus 1 times k plus 1 factorial. In other words, I just have to do a little bit of algebra. The only trick to this is that I don't actually know the value of f of x. So I don't really know the value of m, but I know there is one. And that's the key. It's unknown, but it definitely exists. And now we're about to do something really clever. Let's examine the values of h at c and at x. Well, h of x we already know. It is 0 because that's the way I picked m.
So we assume h as equal to 0.
We picked m to force h of x to be 0.
Oh.
Yep. But h of c is equal to f of c minus tk of c minus nothing, because c minus c is 0. And you may remember that the way that we constructed our Taylor polynomials was using the best estimate requirement, that the Taylor polynomial agrees with the function right at c, so that h of c is necessarily 0 also. Well, what do I have? I have a function that has two values the same, 0. Is my function continuous and differentiable? Well, yes, because h prime of x is equal to f prime of x minus tk prime of x minus, now here's where I actually have to take a derivative. It's going to be the derivative of this term right here, which is going to be m times all that. And so my function is differentiable because f is differentiable, tk is differentiable, it's a polynomial, and of course the last term is differentiable also. So what I conclude then is I have a function with two equal values, it has a derivative, it's continuous, I can apply Raleigh's theorem to it. And when I apply Raleigh's theorem, it allows me to conclude that there is a t, let's call it t1, somewhere between c and x, such that h prime of t1 is equal to 0. If we're tracking on a number line, here's my center c, here's my value x, and somewhere in here I found a t1 so that h prime of t1 is equal to 0. Okay, we like that. That's fine. It doesn't give us a lot of insight yet. But now, observe. What happens when I compute h prime of c? Well, h prime of c, of course, is going to be f prime of c minus tk prime of c minus all this. Is it okay with you if I cancel my factor of k plus 1? K plus 1 over k plus 1 factorial is the same as k factorial. Oops, I forgot. I'm evaluating at c. So it gives me c minus c is okay. Well, what is this equal to? This last term is obviously 0. These two terms are exactly equal to each other. Why? Because the Taylor polynomial is constructed so that its first derivative is equal to the first derivative of the function at c. That's the best estimate criterion. And so this is also equal to 0. Now look what we have. We have a function that is continuous and differentiable, that's h prime, and it has two values equal to each other, equal to 0, c and t1. So I can apply Raleigh's theorem to them, and I can conclude that there is a t2 somewhere between c and t1, such that h double prime of t2 is equal to 0. Cool. I think I smell a pattern coming. So what I did was I found a t2 somewhere in here, so that h double prime is equal to 0. Wow! I've got a value for which h double prime is equal to 0. And I'll bet you can tell that there's going to be another one. And it's going to be right at c. If I evaluate h double prime of c, well, let's find h double prime of x first. That's f double prime of x minus tk double prime of x minus m times. Here I take the derivative and my factor of k comes down, canceling with a factor of k and leaving me with k minus 1 factorial, just like so. And when I evaluate h double prime of c, lo and behold, that's f double prime of c minus tk double prime of c minus nothing. And these two are equal because of our best estimate criterion, so that h double prime of c is equal to 0 also. This being the third time that you've seen this, you have certainly called on, except for Devlin, who's sleeping. Wake up, sir. And so we have a function that is continuous and differentiable, and it has two equal values at t2 and at c, so we apply Raleigh, and what will we conclude from Raleigh's theorem? There exists a t3 such that what? That's exactly it. And so we like that. Well, we can see this pattern is going to go on until something happens. What is that something? Well, that something is going to be that tk is going to run out of derivatives. So let's continue this pattern on down until we hit the point that there exists t sub k somewhere in c to t sub k minus 1 such that the kth derivative of h at tk is equal to 0. And let's figure out what that kth derivative would be, and then we'll get a little bit of insight. That kth derivative is going to be the kth derivative of f minus the kth derivative of tk minus m times, check our pattern here, two derivatives give me k minus 1 factorial. The k derivatives is going to give me just 1 factorial. 2 here, we start with k plus 1, subtracted 2, k derivatives will subtract, yep, 2 to 1 power. And this is the end of the line, because when I evaluate at c, I get the kth derivative at c, I get the kth derivative at c, minus nothing. This is still 0 by the best estimate criterion. And that allows me to conclude one last time that there is a tk plus 1, which I'm going to relabel as t, such that the k plus 1 derivative at t is equal to 0. I'll finish this out in 1 second, and then we'll turn you loose. All of this is in your handout, by the way. So I compute the k plus 1's derivative, and here's where the k plus 1's derivative of my Taylor polynomial is 0, because it's a k-degree polynomial. And the k plus 1's derivative of x minus c to the k plus 1 is over k plus 1 factorial is just 1. So that since this is equal to 0, I have exactly this guy is equal to m, but what was m to begin with?
0.
M was this fellow right here, so that I conclude that my remainder of x is going to be equal to, exactly equal to that times m, which is x minus c to the k plus 1 over k plus 1. In other words, I found the exact remainder.
Okay.
When I use, I don't know where t is, so I use my worst case assumption to do the math. I'll see you tomorrow.
Where's the assumption?